right, so hi everyone. It's good to be back again for the next session of the Quarantine Thermo seminar series. So we're very happy to have a special guest here. It's Nicole Halpern. So Nicole is currently an ITAP fellow with a joint affiliation between Harvard and MIT. As you can see in the background, this is my native West Cork, Beara Peninsula. Unfortunately, I can't go there in person for this lovely weather Easter weekend in Ireland, but you know we can only think of that. So yeah, let's just say that I hope that everyone is feeling good and is keeping safe and all that. And today Nicole is going to give a presentation. So Nicole, without further ado, I'd ask you to share your slides. I'll drop out and I'll contact you if there's any problems with the stream. Okay?
Okay, here we go. Great, can you see my slide?
I can see your slide. I mean, if I could just ask you to bring it to the front and maybe drop your own picture out because your picture is up on the right-hand side.
Let me see.
I mean, maybe just minimize your picture, Nicole, is the easiest thing. So, you know, in the Zoom window on the
like
upper right-hand side, you're
yeah. So the picture of me that you're seeing is not on my screen.
Okay.
It's just on yours.
But that's the point, that means that it's coming up on the stream. So if you could just minimize that, it would be great.
Well,
no, it's wait. Yeah. Okay. That's actually me. Sorry, I thought it was you. So that's perfect. I think it's all good now. All right?
Okay, great.
Take it away.
And thanks very much for the opportunity to talk with you guys. Thanks to everybody for joining from the various time zones around the world. I'm honored to have the opportunity to share with you, and very, very special thanks to the group in Dublin. I think it's fantastic that the seminar series has been organized, and it's a great boon for the quantum thermodynamics community, so thank you for that. A lot of us have been sitting at home for a while, so I'd like everybody to, in your respective homes, stand up. Now, John, are you actually able to see the video of me? John, are you there?
I have to come back to the room. I'm watching a YouTube stream in another room. Nicole, what's the issue?
Okay, I wanted to check whether you can see video of me because that's somewhat important to parts of the presentation.
At the moment, I just see a white screen.
Okay, then this will be particularly difficult to illustrate, but let's give it a try. Okay, so I hope that everybody is standing up. I would like to go through a new dance move. Don't worry, it's an easy move. I call it the Photo Isomer. So photoisomers are small molecules. So put your hands up. Each of your hands is going to represent one of these circles that you see. And each of the circles represents a chemical group in this small molecule. So put your hands all the way up. We are in the cis configuration. So suppose that, now this is what's difficult without video of me. Imagine that I'm standing in front of you and I turn so that you're looking down my side. As far as you can see, my hands are directly on top of each other. So 0 degrees separate my chemical groups. So this is the cis configuration. Now, for those of us for whom it is still daylight, light is shining on us. And when light shines on a photoisomer, it has the opportunity to be a molecular switch and switch configuration. So without hitting anything next to you, I want for you to rotate one of your arms all the way downward. This configuration is called the trans configuration. So again, if I were to stand in front of you and turn my side towards you, you would see 180 degrees separating my chemical groups. So again, put your hands up in the air. Now wave them around like you just don't care. That isn't necessary for molecular switching, but I just wanted for everyone to go through that. And now do the photoisomer. Rotate one arm downward. Okay, I hope that was done across the world. If you did it, thank you very much, and you can be seated. So why did I put you through this torture? Because photoisomers are prevalent and useful. They are in nature. For example, they are in our eyes as retinol in the protein rhodopsin. And they're in technologies. They're relatively easy to code for genetically and relatively easy to create. For instance, an experimental group at collaboration at Harvard and MIT took these graphene nanotubules and stuck photoisomers on the nanotubules to enhance the ability of these structures to store solar fuel for a reason I'll explain. Since photoisomers are so prevalent and useful, we are compelled to ask, how effectively can these molecular switches switch? This question is difficult to answer because photoisomers are small, quantum, and far from equilibrium. So we have some models for them, but um, they're in detail difficult to model. We might think that we need to make assumptions to make headway, but some of the assumptions are not always palatable. So we would like general, simple thermodynamic style bounds on probability that a molecular switch switches. And the switching probability is called the photoisomerization yield. Fortunately, resource theories for thermodynamics in this case come to the rescue. The resource theories, as many of you know, are very simple models developed in quantum information theory for any situation in which there are constraints that restrict the systems you can access and the operations you can perform. In the context of thermodynamics, resource theories have recently been used to extend the laws of thermodynamics to small scales, to quantum systems, and far from equilibrium. Resource theories for thermodynamics involve few assumptions, namely the conservation of energy, the first law, that the environment is at some temperature, which is basically Markovianity, and quantum mechanics. Most resource theory papers have the style of theorem, lemma, theorem, corollary, which is a lot of fun. I love those papers. I write them too, and they should definitely be written. We might also, from a different perspective as resource theorists, want for resource theories also to do something else. We could imagine that resource theories could connect to the real physical world and also do good for the broader scientific community outside of our, uh, our cohort of quantum information theory and quantum thermodynamics. I've been harping on this for a number of years now. I've talked with a number of you about this, and I'll talk later about some of the other steps that have been taken in this direction. Most of the talk is going to focus on one of the works that takes quantum resource theories and quantum thermodynamics, in particular thermodynamic resource theories, into the rest of science, in particular chemistry. So suppose that we have an idea. We could take a photoisomer and model it within a thermodynamic resource theory. Then pluck from the thermodynamic resource theory literature the right theorems to apply to our photoisomer in order to bound the probability that the molecular switch switches. And also, we could characterize the role played by coherence relative to the energy eigenbase in the switching process. We would be using a thermodynamic resource theory to answer a pre-existing question in chemistry. That's the mission that I took on with my collaborator, David Limmer, who is a chemist at UC Berkeley. He actually independently had this question, how effectively can molecular switches switch? And together we answer the question with a resource theory. Here's where I'd like to go in the rest of this talk. First, I'll give more background about the photoisomer, this molecular switch. Then I'll give background about thermodynamic resource theories, and then we'll put them together in the main results. We'll model the photoisomer in the resource theory and bound the probability that the molecular switch switches using the right theorem from resource theories. I'll also argue that coherences of the electronic degree of freedom relative to the energy eigenbasis can't increase the switching probability. I won't say very much about the other results that we have. I'll focus on the main result, but I'll mention this briefly in case anyone's interested, and I'll talk about the opportunities opened up by this work. So let's start by learning more about the molecular switch. The molecular switch has an energy landscape that can be modeled like this. First, focus on the x-axis. That's labeled with this parameter phi, which is the rotational coordinate that parameterizes the angle between the chemical groups, or the angle between your two hands as you're rotating one arm downward earlier. There are two particularly important configurations that we saw when your hands are up together, both of them over your head. then the two chemical groups are relatively near each other. This is the cis configuration. And when 180 degrees separate the chemical groups, then you're in the trans configuration. This rotational coordinate is a nuclear degree of freedom, so it's heavy and slow. It determines the energies and the energy eigenstates accessible to the electronic degree of freedom, the light, fast degree of freedom. Suppose that we choose we fix the angle between the two chemical groups. That's like taking a slice out of this diagram that determines the energies and energy eigenstates experienced at that time by the electronic degree of freedom. This electronic degree of freedom can be approximated as a two-level system, an effective qubit. Here's what happens during the process of photoisomerization. So the molecule begins at thermal equilibrium at room temperature. That's well approximated by this lowest energy eigenstate. Then some light shines on the system. For example, an ultra-fast femtosecond laser. Some energy and coherence could move from the laser into the molecule so that the molecule is photoexcited. It's still in its cis configuration, but up here it has the opportunity to rotate while sliding down this energy level. In order to pass through this crossing, the molecule needs to get rid of energy. So it's coupled to a bath. This is actually a dissipative Landau-Zener transition. And in the best case, the molecule will end up down here on this metastable level. It's separated from the lowest level with this little hill. This metastable state is useful, for example, for energy storage. Suppose that it was a photon from the sun that photoexcited our molecule. Then the molecule can store the energy in the photon for a time that's like the life of this metastable state. We've talked some about the photoisomer. Now let's give some background about resource theories, which a lot of people in the audience, I'm pretty sure, are very familiar with, but not everyone, so let's make sure we're all on the same page. First, just generally, what are resources? I'd like for everyone to think of some examples of resources in your life and in the broader community. I guess nowadays masks are a big resource. Face masks. In general, resources are things that are valuable, useful for tasks, and scarce. For example, if you have the resources of memory and time, then you can perform the task of solving computational problems. Or if you have money, then you can buy lab equipment. Or if you're a theorist, you can buy coffee. And sleep is a resource that's necessary for basically everything. Since resources are useful and important very broadly, we might want to answer some questions about them. We might want to be able to quantify resources, to compare which resource is greater than which other resource, to identify which resources can transform into other ones via easy processing, which resources can't transform into which, and what you would have to pay in order to make an impossible transformation effectively possible. In general, we want to distinguish what is possible and what's impossible. To achieve those goals, we use resource theories, which are simple models developed in quantum information theory for any context in which constraints restrict the operations you can perform and the systems you can access easily. For the systems that you can access, we call free systems. For example, consider thermodynamic processing in a temperature T atmosphere. It is arguably relatively simple to get a system that is at thermal equilibrium relative to the environmental temperature. The operations performable are called free operations. For example, in thermodynamics, we are restricted to obey the first law of thermodynamics to conserve energy. Everything that isn't free we call a resource. In this specific thermodynamic example, states that are not at thermal equilibrium relative to the ambient temperature are resources. How come? Well, we can illustrate with a simple example. Suppose that we are in an environment at a fixed temperature T sub h. We have access to a giant heat bath at T sub h, and all of a sudden we're given a much colder system. We can let heat flow from one to the other. From the heat flow, we can extract work. Work is valuable. For instance, we can use it to power our cars. So it makes sense to think that the system that is not at thermal equilibrium relative to the ambient temperature serves as a resource. Suppose that you want to model your favorite thermodynamic system in a resource theory. How do you do that? I'm going to restrict the discussion to resource theories that model exchanges of just heats with other systems, though there are generalizations that I sometimes talk about in other settings. But this is all we need for our particular problem. We specify a system by specifying a Hilbert space curly h, and a density operator rho, and a Hamiltonian h defined on that Hilbert space. We often speak in terms of a thermodynamic agent who's given access to a bath at an inverse temperature beta. The free states are the states at thermal equilibrium relative to the ambient temperature. So we think of the agent as able to dream up his or her favorite Hamiltonian H sub b and pluck from the environment a system governed by that Hamiltonian and at thermal equilibrium relative to that Hamiltonian and that inverse temperature. The free operations are called thermal operations. At least these are the free operations that we will focus on. There have now been a number of classes of free operations attributed to thermodynamic resource theories that model just exchanges of heat. The classes are fairly closely related to each other. Some are a little more general than others, but thermal operations are pretty simple, and they're all that we'll need to solve our particular problem. Unsurprisingly, these operations tend to bring states down toward thermal equilibrium. So each free operation consists of 3 steps. You can draw any equilibrium free state from the bath and bring it over to the system of interest. You can couple the two together with a unitary that conserves the total energy, and you can discard a subsystem, an ancilla, that is not coupled to the rest of the system. So mathematically, a free operation looks like this. We start with some system rho comma h. We can bring over a piece of the environment, couple the two together with a unitary that conserves the total Hamiltonian. By the total Hamiltonian, I mean Hamiltonian of system plus Hamiltonian of bath, because the interaction Hamiltonian is what's generating this unitary U. This is the manifestation in the resource theory of the first law of thermodynamics. Finally, we can discard a subsystem A that's not coupled to the rest of the system in the Hamiltonian. So this is how the state transforms. We transform the Hamiltonian by taking the Hamiltonian of the system, adding on the Hamiltonian of the bath, and subtracting off the Hamiltonian of the ancilla. Now, let's put these two pieces of background together and model the molecular switch in the thermodynamic resource theory. We attribute to the molecule a Hilbert space that has an electronic component and a nuclear component. The Hamiltonian will write like this. So first, there is a rotational kinetic energy of that nuclear degree of freedom. The rotation can happen at each of many different angles phi in between the chemical groups, so we'll integrate over those. We said that when you fix phi, the angle between the chemical groups, you effectively take a slice out of this energy diagram, determining the Hamiltonian experienced by the electronic degree of freedom. As a side note, for those who are familiar with the formalism of quantum clocks in quantum foundations and resource theories, this Hamiltonian has the form of a quantum clock, an imperfect quantum clock because perfect quantum clocks can't exist. Also, the state of this system is amenable to being modeled with a clock. So it seems like this is a realistic quantum clock that is simply out there. But let's take that process of photoisomerization and model it with thermal operations. We start off with the molecule and the light source. The molecule is at thermal equilibrium at room temperature, and the light source is in some state, whatever state, maybe a coherent state. During the first thermal operation, energy and maybe coherence move from the light source into the molecule. I'm going to take advantage of that third step of the thermal operation, namely tracing out an ancilla, to trace out the laser from our system. So we're left with the state of the molecule. By the way, from now on, anytime I say coherence, I'll mean coherence relative to the energy eigenbasis. So this is the state of the molecule after the excitation. The electronic state could have coherence between these two energy levels, and the molecule is in its cis or phi equals 0 configuration over here. During the second thermal operation, the molecule rotates, and you can actually better model this thermal operation as a sequence of thermal operations that compose into one giant composite thermal operation. We also have a more detailed model of those little steps. After this rotation, the molecule's in a probabilistic combination of being in the cis and trans configurations. So I'll model the entire molecular state with this sigma. We want to know the greatest probability that the molecule ends in this metastable level. To answer that question, we'll use some results from the resource theory framework that are sometimes called second laws of thermodynamics. How does the second law manifest in conventional thermodynamics? We often have some system in a macro state, for instance, a gas in a box, such that the particles are all clumped together in one corner of the box. Then we'll have in mind another macro state, for example, that in which the particles are spread all across the box. We'll ask, can this system transition spontaneously from one state to the other? To answer this question, we identify the relevant free energy. If the gas can exchange heat with a fixed temperature bath through the walls of the box, then the relevant free energy is the Helmholtz free energy. If and only if the free energy declines monotonically, the transition can happen spontaneously. And when we tell this story, we implicitly have in mind equilibrium states, a very large system, and the opportunity to average over particles and over trials. We might want to back away from those assumptions. So let's restate the question in the context of the resource theory. Now we have in mind an initial system, rho h, and a final system, sigma h prime. Now we'll ask, does any free thermal operation map one to the other? We're asking a more general question, so we have to do more mathematical work. We can't just check one inequality, we have to check a whole set of inequalities, which are sometimes called second laws. In fact, there are two subfamilies of second laws. And I should add that some of the subfamilies can have different forms depending on the context. The one subfamily of inequalities governs the energy diagonal of the states. So this is the question that we asked abstractly. Each state is a density operator that we can represent as the matrix relative to the energy eigenbasis. So the diagonal elements are the probabilities. The probabilities that if you measure the energy, you will get a particular outcome. These obey one set of second laws. The off-diagonal elements are coherences relative to the energy eigenbasis. Those obey another family of second laws. We are interested in bounding a diagonal element. Let's start applying the second laws of thermodynamics to our molecular switch. Here's the question that we asked abstractly in the context of the resource theory. Let's instantiate it in the context of the molecular switch. The initial state that we'll be interested in is the state of the molecule after excitation by the laser. The final state is the post-rotation state. And the Hamiltonian is the same for both cases, which is the one that we wrote out earlier. We'll simplify this model to an effective four-level system because we're only interested in the cis and trans configurations, because over the timescales of interest, the molecule tends to localize in those configurations. So cis configuration and the trans configuration each corresponds to one nuclear state. So these two nuclear states each correspond to two electronic states. 2 times 2 equals 4. First, we'll use this theorem about the coherences. We can take a density operator and break it into modes, each defined by an energy gap. So suppose that we write our density operator like this. Suppose that the set J is the set of energy eigenstates. We can decompose the density operator in terms of the energy eigenbasis. Now, the omega mode of the density operator is defined as a sum over these coefficients rjk, such that j and k correspond to energies separated by a gap omega. So that's the omega mode of this state. Now, our density matrix relative to the energy eigenbasis has along the diagonal what could be called the zero mode. These probabilities are not coherences as we usually think of coherences. We could think of them as the zero mode. So a theorem states that these modes all transform independently under thermal operations. more or less the basic physics behind this is Markovianity. The temperature or the environment is always at a fixed temperature and in a thermal state. What implications does this theorem have for the photoisomer? We said we wanted to bound a diagonal element to the density matrix, a probability of getting into a particular energy eigenstate. Coherences cannot affect that probability because the coherences transform independently. So, our bound on the probability will depend on just the diagonal elements of the states. So, in our calculations, we might as well just replace the states with states decohered relative to the energy eigenbasis. For instance, this is how we represented the initial states. Consider decohering relative to the energy eigenbasis. We get just these probabilities, R plus and R minus. So we'll focus on those. Similarly, the final molecular state is sigma. We will focus on the probabilities S minus and plus, cis and trans. Now that we have allowed ourselves to focus on the energy diagonal, let's look at the second laws for the energy diagonal. The mathematical toolkit behind this result is called Demajorization. Here's how we check whether one system can transform it into another system via thermal operations. I'm going to set the two Hamiltonians equal to each other. The abstract result can be generalized, but this is all we need in order to solve our molecular problem. First, we take one of our states, we identify those energy probabilities, the diagonal elements, and we rescale them with inverse Boltzmann factors. Each probability encodes an informational resource. It tells us how likely we are to be able to predict the outcome of a measurement. This inverse Boltzmann factor encodes an energetic resource. So by rescaling the probabilities, we create a mathematical object that includes all the thermodynamic resourcefulness of this system in a fixed temperature environment, an informational resource and an energetic resource. And we take the rescaled probabilities and order them from greatest to least. Then we plot partial sums of the probabilities like this. On this plot, I want for you first to focus on the x-axis, which has a number of tick marks. One tick mark is at the origin. To get to the next tick mark, we add the first Boltzmann factor. To get to the next tick mark, we add the next Boltzmann factor, and so on and so forth until we've added all the Boltzmann factors and gotten z, the partition function. Each tick mark is going to be associated with a point. We get the point's y-coordinates like this. One y-coordinate is again at the origin. To get to the next y-coordinate, we add the first probability. To get to the next y-coordinate, we add the second probability, and so on and so forth until we've added all of the probabilities and gotten 1. Well, now we've plotted a bunch of points. We connect the points with straight lines, and we have a Gibbs rescaled Lorenz curve. This is a geometric representation of all the resourcefulness, informational, and energetic in this state in thermodynamics. The more that this curve bows away from the diagonal, from the origin to the upper right-hand corner, the more value this state has. Now let's compare two states. Let's plot their curves on the same plot. We use this theorem, which states that there exists a thermal operation that can transform one system into the other system if and only if the rho curve lies everywhere above or on the sigma curve. In this example, the rho curve does lie everywhere above or on the sigma curve, so yes, the transformation can happen. We do say everywhere, so that statement encodes a whole bunch of inequalities. Again, we were asking a more general question than the conventional thermodynamic question, so we have to do more mathematical legwork. We can't just check one inequality. Let's take those second laws of thermodynamics for the energy diagonal and apply them to our molecular switch. Here's the strategy that we'll employ. We said that the initial state in our mathematical problem is the state of the molecule after excitation by the laser. Now, a laser can excite a molecule to any of many possible states, so we'll consider a range. For each possible initial state, there are some possible final states. 4 parameters parameterize the final state. We'll plug all of those parameters into the second laws for the energy diagonal, and then we'll solve for the greatest probability, S minus trans, for which the rho curve lies everywhere above or on the sigma curve. I'll show you our results. To do that, I'll introduce one more parameter. It's this little delta E, which is the energy gap between the lowest energy state and the metastable state. We'll assume that this gap is small, much smaller than the gap across which the system is photoexcited, and that is physically realistic. Now I'm going to show you some plots. Along the x-axis, I'll show you this little energy gap rescaled with the inverse temperature. Along the y-axis, I'll show you bounds on the probability that the molecular switch switches. First, suppose that the laser is very, very good. So it completely photoexcites the molecule all the way into this upper energy eigenstate. Then on our plot, this blue curve represents the upper bound from the resource theory, and that bound is trivial. There's an upper bound of 1 on the probability that the molecular switch switches, which sounds silly, but we can understand it by breaking down the problem in terms of resources. This initial state has a lot of informational resource because it's an energy eigenstate. If we measure the molecule's energy, we know exactly which outcome we'll obtain. Furthermore, this is a high energy eigenstate. So this state has a lot of informational and energetic resourcefulness. So it makes sense that the basic thermodynamic constraints of energy conservation and a fixed temperature in quantum mechanics won't pose too much of a problem for the molecules being able to switch into the metastable lower state. This red dashed curve is a lower bound from equilibrium Boltzmann factors. So with our upper bound and our lower bound, we are constraining the probability of switching. Now, suppose that the laser is just so-so. It manages to excite just half of the probability weights of the molecule to the upper level. Now, our resource theory bound is lower, as we expect. We can understand that by comparing this so-so initial state to the good laser initial state. To get from the good laser initial state to this initial state, we have to transfer some probability weight downward. As we transfer probability weight, we decrease the informational resourcefulness of the state, because now, if we measure this molecule energy, we don't know which outcome we'll obtain. Second, as we're transferring probability weight downward, we're also decreasing the energetic resourcefulness of this state. So this state has less energetic and informational resourcefulness, and makes sense that our resource theory bound is lower. Now, suppose that the laser is quite poor. So it barely excites the molecule at all. You might think that the molecule has basically no hope of getting into the metastable state. But if the gap is small, then actually the probability can be fairly high. Again, we can understand that behavior by thinking in terms of resources. Sure, this state has little energy, but it has a lot of information because the system, the molecule now, is in a nearly pure energy eigenstate. So if we measure the molecule's energy, we have a pretty good idea of which outcome we'll obtain. This informational resourcefulness makes up for the dearth of energetic resourcefulness, provided that the gap isn't too big. If the gap is pretty big, then the probability gets squeezed more and more, and our bounds become tighter and tighter. Those were the results that we got from this abstract resource theory, and we wanted to compare them with a more detailed model. So we came up with a toy model of a particle hopping amongst 4 energy levels in contact with a bath. We used this Lindblad master equation. This first term on the right-hand side is basically encoding closed system evolution. The final term encodes the action of the bath. This Lindbladian consists of the operation by Lindblad operators. These transfer probability weights in between levels, so they mix up energy levels. That's what this term does. It mixes levels, and this term preserves the norm of the state. These gamma sub i's denote dissipation rates. They satisfy detailed balance, so they check out against our expectations about thermalization. Let's look again at our 3 parameter regimes. Suppose that the laser is good, So it photoexcites the molecule all the way up to this cis configuration excited level. I'm going to label the energies like this. The configurations are labeled by the corresponding angles between the chemical groups. So the phi equals 0 corresponds to the cis configuration, phi equals pi corresponds to the trans configuration. Each lower level is denoted by an E minus, and each upper level is denoted by an E plus. I'm going to show again some plots. Along the x-axis, I'll plot the time, rescaled by dissipation rates. And along the y-axis, I'll plot the probability that the molecule at a particular time is in a particular energy eigenstate, specified by plus or minus and the angle phi. Let's focus in this plot first on the red curve. That's the photoisomerization yield. It's the probability that the molecule is in that desirable metastable state. That probability starts out very low because we have just excited the molecule into the upper cis level. But after a short time, the molecule is quite likely to switch. And after a much longer time, the molecule thermalizes back to this original thermal equilibrium state. So we actually found a realistic parameter regime that saturates the resource theory bound, which is represented by this gray area. So the resource theory bound looked kind of trivial in the case of the good laser, but in a realistic regime, it looks like it can be saturated. Now let's move to the so-so laser that excites just half of the probability weight of the molecule state. Now, the photoisomerization yield, the probability of getting into the metastable state, again, starts out small as expected because the molecule does not begin even in that final configuration, but it grows over a short time scale. And again, because of the meeting of red curve with the top of the gray area, we see that the resource theory bound is saturated. And then after a long time, thermalization happens. Now suppose that the laser is bad, so it barely photoexcites the molecule at all. Now, the resource theory bound can be saturated, but only at long times because thermal fluctuations are driving the isomerization. Some takeaways from these results are we have derived fundamental limitations from just the basics of thermodynamics on the probability that this molecular switch switches. If the laser is poor, as in, for example, the experiment that I mentioned earlier, the resource theory bound actually constrains the yield tightly. We can always understand the bound by reasoning resource theoretically in terms of energy and information. We can come up with a more detailed model in which a realistic looking parameter regime exists such that the resource theory bound is saturated. We also argued that electronic coherences relative to the energy eigenbasis cannot help with the switching. And there were some other fun little results that we got from applying other resource theory theorems to the photoisomer. I'll just mention them briefly. As I said before, it looks like the molecular switch serves as a quantum clock. I would be really interested in talking with anybody interested in quantum clocks about whether we could use this to our advantage. There are a lot of people in foundations and resource theories who think about quantum clocks, and separately, there are people in, say, GILA and experiments who think about quantum clocks. And it could be really cool to connect to the communities. These photoisomers do exist out there, they're easy to make, and we have great control of them because of ultra-fast femtosecond lasers. So I would be really interested in hearing whether anyone thinks that there's an opportunity to use what look like natural quantum clocks that fit the resource theory formalism for a quantum clock, but are really controllable experimentally. We can calculate the minimal work required to photoexcite the molecule in a single shot to a given state. Also, there are some results in the resource theory framework stating that you can extract work from the coherences of a state relative to the energy eigenbasis under certain conditions without changing the probabilities relative to the energy eigenbasis at all. And we found a toy situation in which, in principle, it seems that that can be done with a photoisomer. And also we can quantify the energy coherences in the state after the rotation. So there's some opportunities opened up by this work. One is, again, if anyone is interested in talking about molecules as quantum clocks, I'd be happy to do so. Also, something that has been on my mind a lot for a number of years is connecting thermodynamic resource theories to physical reality. I wrote this paper a few years ago, talking with a number of members of the community. Um, a lot of us in thermodynamic resource theories love this style. It's very good mathematics, a lot of fun, and gives great insight into really fundamental questions about the basic laws of thermodynamics and how they extend. Um, we can also think, what if, now that we have these results, can we take them and apply them to the broader scientific realm? So I talked about some that challenge and some of the opportunities there in this paper. Um, I'd now like to point out a number of the other steps that have been taken with the community, taken within the community along this direction that I found really exciting. First, there have been some proposals of experiments designed to realize results within the thermodynamic resource theory framework. And there have been also some other steps in trying to take resource theories and make them more physically realistic, or take them and apply them to other settings, other quantum settings. So, in general, I'd like to challenge the community to take our toolkit and use it to transform science broadly outside of quantum information and thermodynamics. Um, and in particular, ask, what are open questions that exist out there in the broader community? We have developed together some very cool mathematical and conceptual tools. Can we use them to solve other people's problems? And um, on the one hand, there's one part of me that is very much devoted to this sort of abstract mathematical way of thinking. But can we take this way of thinking and apply it to real physical systems to get new insights into problems out there in the wild? So some possible settings, a limited list, include um, exciton transport in films made from quantum dots. So there are films of quantum dots, light hits the film, the light creates excitons that hop around the film, and eventually the energy from the excitons is gathered and stored. Photovoltaics, in some ways, have some structural similarities with photoisomers, and that transition that I mentioned during the switching process of the molecule is a dissipative Landau-Zator transition. We created a molecule for this dissipative Landau-Zator transition within the resource theory via thermal operations. Landau-Zator transitions are very prevalent across condensed matter and chemistry code. So, could this resource theoretic model for them be used to merge this resource theory framework with chemistry and material science and condensed matter more? And there, I'm sure, more examples that I'm missing. So in summary, we learned the new dance craze sweeping the chemistry and quantum information community, the photoisomer, which is a small molecular switch that is in us, in nature, and in technologies. We reviewed thermodynamic resource theories, which are very simple but very powerful mathematical toolkits developed within quantum information. We saw how to model our favorite thermodynamic system, and we reviewed some sets of second laws of thermodynamics. The main results consisted of modeling this molecular switch within a resource theory and using the right theorems to bound the probability that this molecular switch switches. And we saw a few other little fun side results in that there's a lot to be done. So thanks very much for your time.
Nicole,
Hi, John.
are you done?
Yes.
Okay, good. Sorry, there was a slight delay because I was watching it on the other. Let me just come into the call.
No worries.
So the talk was excellent. Thank you very much.
Thanks.
I unfortunately, because I'm always paranoid about this streaming rate,
Mhm.
I let's see if I can win. Yeah, I basically I miss a lot of the talk myself, unfortunately. So I
I
have to go
understand.
back and I have to look at the thing afterwards. So look, listen, it seemed really clear. There was a little bit of
Great.
jittering at the start, but overall the stream was quite good, I think, for most people.
Okay,
Um,
great.
so listen, I'm looking at the YouTube stream. We didn't have a question during the talk, but maybe I can ask people if they have a talk now. I have a question now. Sorry, excuse me.
Sounds good.
Let me just see. It doesn't seem to be. Okay. I'll just wait for it to come through. There's a delay, you see. So I mean,
Mhm.
takes a bit of time. I'm just keep an eye on it. Okay. Da-da-da. So have you been talking to any experimentalists about this, Nicole? Like with femtosecond stuff and.
This particular project, let's see. Um, Ono, I've been talking with Ono Pusiluk, who's, you probably know him since there's the shared Latko connection.
Okay.
Um,
Yeah, the name is
he,
familiar.
he contacted me a while ago. He also has a really nice paper on using quantum information theoretic thinking to apply to proton transport in molecules.
Okay.
And he a while ago said that he would look into seeing whether maybe Tristan could do an experiment based on this. I should contact him again about that.
I see. So, any more questions, guys? I'm just maybe there's a bit of a delay. Let me just get my keyboard for the iPad. Hold on. Just hold tough, Nicole. My 3-year-old threatened to interrupt your talk at one point. I had to intervene. It's actually quite delayed. I can see in the YouTube. So Archak, who works here in Dublin in our group, has a question. Can you explain in more detail the concept of a photoisomer as a quantum clock? And then he says, I know almost nothing about quantum clocks. What are quantum
Okay,
clocks, Nicole?
sure. Let me find the right slide first. Okay, got it. Then I'll share my screen.
Okay.
And enter full screen mode. There we go. So can you see my slide?
Yeah, let me just pop you out of the window slightly.
Let me know when I should go on.
Yeah, go ahead. I think Archak is waiting. Thanks for the
Okay.
question, Archak.
Yes, thank you. Okay, so here's the idea of a clock. It has hands. The hands move downward or move around, and the position of a hand dictates what is going on. So when a clock hand points to 5 o'clock, you might be asleep unless you have small children.
Yeah.
At 10 a.m., when the clock hand points to 10, then you might be listening to a lecture. Hopefully, you are not doing the two of them, sleeping and listening to a lecture right now. So, similarly, our molecular switch has this chemical group that rotates downward. And we said that this Hamiltonian is a model for the molecular Hamiltonian. So there is this rotational kinetic energy term that encodes the rotation of this quote clock hand. And we said that if you fix the clock hand's rotation, so you fix phi, the angle in between the two chemical groups, then you fix the Hamiltonian being experienced by the electronic degree of freedom, which is like fixing the sort of evolution during a particular time of our individual. At one time at 5 a.m., the person is sleeping. We could imagine that as sort of one Hamiltonian, and the being in a lecture is sort of like being governed by another Hamiltonian. So that's a parallel between our molecules Hamiltonian and clock Hamiltonian. In a little more detail, there's been a whole lot of work recently and across the decades, really, about quantum clocks. Why does it make sense to think about clocks in thermodynamics? Well, clocks measure time, and time is conjugate to energy. Energy is what we talk about in thermodynamics. Um, in fact, this clock Hamiltonian that I showed here is, as I said before, an imperfect clock Hamiltonian. The ideal perfect clock would have this proportional to not the angular momentum squared, but the angular momentum. So that the angular momentum would, when evolving the state of the system, would just would just kick the location, the phi degree of freedom of the clock hand. So if you had the Hamiltonian proportional to just the momentum or the angular momentum, then it would create a little kick and evolve phi forward. Now, such an ideal clock cannot exist because a Hamiltonian proportional to phi would have a spectrum unbounded from below. Such Hamiltonians are not physical. So our Hamiltonian not only kicks the clock hand forward, but also creates a little bit of disturbance to the clock hand. So it's an imperfect clock, but a physically realizable one. Some other important properties that you might want for a clock to have are that the hand is in a relatively well-defined location so that you can basically tell what is the Hamiltonian that needs to be evolving in the system. And also, the clock hand should be moving at a fairly constant rate. So time should be ticking reliably. So we're basically saying that the clock hand should have a pretty well-defined position and a pretty well-defined momentum. That sounds like a contradiction for a quantum system. But if the system is very large, then it could be in an analog of a coherent state. So it could have not perfectly well defined, but a pretty well defined position and momentum. And that is the case with these chemical groups, these nuclear degrees of freedom that are pretty heavy and pretty large. So they're pretty well localized.
Thanks a lot, Nicole, for that very comprehensive answer. So there's a question there from Matteo Lastiaglio. Hi, Matteo. So he says, hi, Nicole. Thanks for the really nice talk. It seems the RT constraints are already tight. So do you think there is no way to improve them by adding extra assumptions such as Markovianity of the dynamics?
Okay. We were supposing in our applications of, oh, and also, yeah, thanks very much for the question, and it's very good to hear from you. I hope you're doing well. So we were supposing in our applications of some resource theory results that the environment is always at a fixed temperature. So you can undergo one thermal operation using an environment at a fixed temperature, and then the next thermal operation proceeds under the assumption that still the environment is at that fixed temperature. It's still in a thermal state. It's always going to be in a thermal state. So we saw that as implicitly encoding Markovianity. If you have any other viewpoints on Markovianity in the resource theory framework, I'd be interested in hearing. We talked with a bunch of people in the thermodynamic resource theory community about what exactly are the assumptions going into some of these theorems. And it did seem to us that since we were assuming that a composition of thermal operations is a thermal operation, and every thermal operation involves an environment at a fixed temperature, we're always assuming that the environment is in this thermal state at a fixed temperature, so there's no memory of the bath is never disturbed, so it is Markovian. Let's see. So yeah, when the laser excites the states just a little bit, that seems physically realistic. And yeah, there the bound is pretty tight. We were thinking about a situation in which making some more specific modeling might help. So I mentioned that there was this paper by some experimentalists at Harvard and MIT. They attached photoisomers to graphene nanotubules. Um, they measured how well their system could store solar fuel, and they expected just a little improvement of something like 30%, but they found a really amazing improvement of something like 200%. So we were thinking, suppose that we model their system with a little more detail. As in, we were thinking about just a free floating photoisomer at room temperature. But suppose you put some model of, say, the graphene nanotubule in, maybe some coupling of photoisomers through the graphene nanotubule or because of proximity to each other. Um, that might be useful because you might be able to get a bound on um, the ultimate improvement that these experimentalists could expect absolutely. As in, they expected a 30% improvement, they got a 200% improvement. So imagine that they do some more. What is the ultimate bound on what they can achieve? And when should they stop engineering because there's no more hope?
I see. Well, thanks a lot, Nicole. Matteo, I hope that answers your question somewhat. I guess Nicole's always available by email as well if anybody wants to ask her questions that come to their mind after the talk. Take a couple of more questions. So Alvaro, hi Alvaro. Yes, thanks Nicole. Since this is a small system in which the equations can be solved, what would you say are the main insights that the resource theoretical constraints give? Bracket, since in principle it seems like you don't need to know the second laws to know if the transition is possible.
Could you repeat the question? I
So he
think I
says,
didn't catch all of it.
since this is a small system in which the equations can be solved, what would you say are the main insights that the resource theoretical constraints give? For example, in principle, it seems like you don't need to know the second laws to know if the transition is possible.
We were interested in a bound on the probability of the transition. So suppose that the molecule is photoexcited by some amount, it could start sliding down that potential energy surface I showed, and it could go either back down into the original well, or it could go into the rotated well, the desirable metastable state. So which of the options occurs is what with what probability each option occurs is something that we would like to know. It is a small system, but it is a quantum system, and it's at intermediate time scales. In particular, the rotation through the crossing is at an intermediate time. It's not extremely fast. It's not as slow as the thermalization. Um, and intermediate time scales prevent us from making a bunch of simplifying assumptions that can help with detailed models. Also, yeah, so non-adiabatic effects are important. And the system is coupled to a bath, and the coupling can be strong. So these are all elements of the setup that can make it difficult to model without making some assumptions that we might want to question whether we really want to make those assumptions. So what the first theory added for us was that it's really simple in general. And it can get us those old like, thermodynamic style bounds that don't depend on really detailed assumptions.
So there's a question that I had in my mind as well, just very quick. Could you kind of maybe mention something about how you want to kind of take into account the vibronic couplings that you typically get in molecules? I mean, if you wanted to extend the theory to really account for like this type of realistic stuff, do you think it's possible or infeasible or whatever?
I think the time scales are separated enough that we don't really have to worry about them here.
That's good. Yeah, that's what I kind of thought, just to make sure. So Karen, hi Karen, how's it going? He asks, say the laser excites two molecules at the same time, generating two correlated excited electrons. Can that or some other collective effect increase the probability of switching? For example, if you allowed for you employed coherences there.
That's a really cool question. We didn't specifically think about that question. We did think about two molecules together. I mentioned that it's been proven that under certain conditions, you can extract work from just coherences relative to the energy eigenbasis without disturbing the populations. Those coherences from which you can extract work are coherences between levels that are degenerate in energy. And one way that you can get levels of a global system that are degenerate in energy is by composing two copies of an identical small system. So we thought about two identical photoisomers, and we came up with a toy situation in which, in principle, it looks like you could extract work from the coherences of this photoisomer. Um, so that's what we were thinking about in terms of how you could use coherences and what happens if you have multiple photoisomers together. I think that that question that was just asked is an interesting question. So if you get any insights, let me know.
Great. So there's a question here that Prazan asked, but then later retracted, but I still think it's worth asking. Um, the question is it possible to use resource theories to rule out or ratify some microscopic models of dynamics for hard to model systems? For example, in your work, you choose Lindblad. I think this is an interesting question, right? So, obviously there's no kind of, there's the really exact way if you've the full unitary dynamics of everything, and you basically try to work out what the map is at the level of the reduced state, but that map could be horrible. The question is whether resource theories could be used to justify modeling in certain situations.
I also think that's a really interesting question. Um, that's sort of it's related to what I was talking about earlier in um, regarding the experimental group. Um, the resource theory offers the benefit of generality.
Yeah.
So if modeling a system within the resource theory is justified, then
Yeah.
you do have fundamental limitations
Yeah, sure.
on what's accomplishable, and
Sure.
so any realistic model should lie within those bounds.
Right, right. I guess it's kind of hard as theorists to understand that an experimentalist in the laboratory, they have some dynamics going on, and the dynamics isn't even completely positive and trace preserving. It's something that's bananas that's going on there because you have initial correlations and everything. So I guess that's a really difficult question to answer in general.
Yeah. So it's just like how justified is your model?
Right. So is there there's another question here by Nathan Myers. Is there an intuitive way to see how the traditional macroscopic versions of the second law emerge in the resource theoretical framework? Thanks, Nathan.
Yeah, a few. This result has appeared in a few papers in a few different contexts. Suppose that we take a different example of a result in the resource theory framework. Um, let's say you can use the resource theory framework to calculate the work required to prepare a non-equilibrium state from just the bath and a battery, and the work that you can extract from such a state. The minimal work required and the maximum work extractable. In the context of conventional thermodynamics, we would expect these work values to be equal to each other. We would run our protocol in one direction quasi-statically, very, very slowly, to prepare to invest work. And then when we would extract work, we would run the protocol backward very, very slowly. And under the quasi-static assumption, each work value should equal the difference between the initial and final free energies. So we can calculate analogs of these work quantities in the context of the resource theory, supposing that the system might be out of equilibrium, it might be small, and then we can ask, suppose that we perform our protocol, maybe work extraction, on many, many, many copies of the system, and then we average over the copies. Then we can use a result from information theory, the asymptotic equipartition theorem, to find that each of those small scale work quantities reduces to what looks like the free energy that we would expect from ordinary statistical mechanics. In the example of a fixed temperature environment, E minus Ts. So there are limits that we can take. We can consider many copies of the system and average over the copies, and use this asymptotic equipartition theorem to get back results reminiscent of ordinary statistical mechanics.
I see. Thanks a lot, Nicole. And there's just one maybe I'll take one last question. So there's a question here about, applications of this type of way of thinking, could you imagine that you could learn anything about real world energy efficient applications? Could you use photoisomers in, for example, solar panels or something like this?
Yeah, I think that's a nice opportunity. What I discussed with my collaborator a little more, although we haven't worked on this, but it was just an idea that we thought could be cool, is the exciton transport that I mentioned, as well as photovoltaics. The photovoltaics share some structural properties. Well, say the problem of photovoltaics shares some properties with the problem of photoisomerization. And I mentioned um, there are films of quantum dots. Light shines on the film. The light shining on the film creates excitons, which hop around and could be gathered up at the edges of the film, so into basically batteries, energy reservoirs. That seems like it also might be amenable to modeling with a resource theory, and some fundamental limitations could be um, calculated. So I do think that there is opportunity in the realm of energy processing.
Okay, so I think we'll kind of wrap it up there. So I'd like to just thank every. Well, there's one more coming in. I'm sorry, but I really have to cut it now. Maybe you can. Sorry, owner. I mean, I have to. I really have to go. I'm already a little bit overdue. But owner, maybe you can actually email your question to Nicole, and you can sort it out amongst us. Is that okay, Nicole? If I ask
Definitely.
people to do that. So look, just to everybody, thanks a lot again for tuning in. Thanks to Nicole for a really great and clear talk. The streaming was much better this time. I hope to have more stuff. I mean, is there a consensus amongst the community of quantum or of quarantine thermo people that we should do something on Friday? It's Good Friday after all. I know it's holiday time, but sort of days are blending into each other now anyway. So I'm not really sure if holidays really make a difference. So I'm not sure whether we'll go ahead one. Why not? Maybe if someone wants to give a talk, we can sort it out. I have nobody lined up yet. There was again of the order of 80 to 100 people tuning in. So looking quite successful. I again just try and encourage people to share the initiative as widely as possible, and in particular, if there are senior members of communities watching this, or maybe people who know senior members of the communities, I'd like to have a blend of younger people and also senior people. So I think it was nice that we had, for example, Ronnie speaking last, and then Nicole speaking next. So you have like a young member of the community and an older member of the community, and if we can keep this going, it'd be great. So wish everyone safe next few days, and see you in a few days. Nicole, thanks very much again for a great talk.
Thanks, John. Thanks for coordinating.
Bye bye.
See you later.